Hello students, good evening. Last video, we had pursued the chapter complex number. What thing we have covered in that video? That the introduction of complex number was discussed, and few basic properties including modulus, argument, the principal value of argument, and the relation between coordinate geometry, complex number, vector were discussed, and while complex number is few steps advanced than coordinate geometry or vector, that also discussed in the last video. Today I will put something more on it, because the depth of complex number is unfathomable. Okay, last year I told you that complex number, the set of complex number is the superset of all number system. So in one video or two video, it is next to impossible to cover up the whole thing. So out of the demand, let's start with few new properties of complex number with different representations and with different types of sums. Okay. So in last video we discussed the standard form of complex number, that is x plus iy. X plus iy means any point in coordinate geometry will be expressed by x plus iy in complex plane. That was taught last year. Okay. Now, in a complex plane contains x-axis and y-axis. In a complex plane, there are suppose 2 points, x1, y1, x2, y2. If you consider this is coordinate geometry, and z1 and z2, if you consider these 2 points lie in complex plane, where z1 is equal to x1 plus iy1 and z2 is equal to x2 plus iy2. Now, if I want to add them, then how to add? What is the rule? In addition, the real part will be added with real part. See, simple horizontal addition, z1 plus z2. Real part will be added with real part plus imaginary part will be added with imaginary part. Okay, so this is the addition of two complex number, 2 points in complex number. Now, one property we were taught in last video, that conjugate of z, that will be z bar sign on the top, z bar. What is that? X minus iy. So here z1 plus z2 means the addition of z1 and z2 resultant. In vector, you are taught resultant vector, AB plus AC, BC. Okay? This Z1 plus Z2 itself a complex number. So, if you take its conjugate, this plus sign, here x1 plus x2 is a component, y1 plus y2 is another component. Means x1 plus x2 is considered as x and y1 plus y2 will be considered as y. So x1 plus x2 minus I y1 plus y2. So z1 plus z2 whole bar is this component minus I into this component. So remove the brackets. x1 plus x2 minus iy1 minus iy. Then you split this part into two complex conjugate. See how x1 minus iy1 will be clubbed in the bracket and x2 minus iy2 is clubbed in a bracket. And see, here you got z1 x1 plus iy1. Then you can write z1 bar x1 minus iy. Okay, x1 minus iy1. That is z1 bar. In the same manner, z2 bar is equal to x2 minus iy2. So instead of this, I can write z1 bar. Instead of this, I can write z2 bar. So we have got a new property. Therefore, z1 plus z2 whole bar is equal to z1 bar plus z2 bar. And it is also true for minus. Okay? In case of division and multiplication, we will discuss it later. So z1 plus minus z2 whole bar, z1 bar plus z2 bar. If you keep on increase the point, say z1 plus z2 plus z3 whole bar, z1 bar plus z2 bar plus z3 bar and so on. Hope you understood. So a complex number z1 plus z2 with bar sign can be split into two parts, z1 bar plus z2 bar. It is true in case of minus also. So I'm rubbing this. I hope you understand. Now, again you take two points in complex plane, x1, iy1 and z2, x2 plus iy2. Now subtract second from first or first from second. Same way, because real part will be subtracted from real part and imaginary part will also be subtracted from imaginary part. z1 minus z2, x1 minus x2 plus I y1 minus y2. Okay, so z1 minus z2 is equal to x1 minus x2 plus I y1 minus y2. So z1 minus z2 itself a complex number. Okay, it's still a complex number. See, in vector you are taught, see, AB plus BC, AB plus BC is equal to AC. Okay, AB plus BC. So AB plus BC itself a vector. Similarly, Z1 plus Z2 or Z1 minus Z2 itself a complex number. Now, you were taught last day that if z is equal to x plus iy is a complex number, then mod z root over of x square plus y square. Yes or no? That is called, mod z in complex number, hypotenuse in Euclid geometry, magnitude of a vector like xi plus yj in vector, and distance formula of the point xy from the origin 0, 0. Now if I take its magnitude or if I take its modulus, what is the formula? Root of x square plus y square. x1 minus x2 whole square plus y1 minus y2 whole square. Now once you get the result, that will reel you back in the past, means in the junior class of yours. This formula we are taught in class 9, distance between 2 points. Distance formula in coordinate geometry. Suppose 2 points are given, x1 minus and x2 y2. Then these points distance is x1 minus x2 whole square plus y1 minus y2 whole square. That is nothing but magnitude or modulus of z1 minus z2. So z1 minus z2 implies the distance between 2 points z1 and z2 in complex plane. So the z1 minus z2 is distance between 2 points z1 and z2 in complex plane. That means the distance formula which you got in coordinate geometry will represent the same concept in complex number. Okay, distance between 2 points. Hope you understood. So from this result, if I introduce one result like this, say z1 minus z2 is equal to z2 minus z3 mod is equal to mod z3 minus z1. If you are getting this result where z1, z2, z3 are vertices of a triangle, then what kind of geometrical figure does it suggest? What kind of geometrical figure? Where z1, z2, z3, where z1, z2, z3 are 3 vertices of a triangle. This means what? The distance between z1 and z2 is equal to distance between z2 and z3 is equal to distance between z3 and z1. So this is nothing but equilateral triangle. So the concept we are taught in class 6 or 7 means 3 sides are equal means equilateral triangle is represented in complex number in this manner. Okay, so don't be confused. Don't be afraid of this complex number new chapter. See, all characters of real number system are also used in complex number, but in different nomenclature, different representation. So this thing represents an equilateral triangle. Equilateral triangle. Okay? Hope you understood. Can I rub it? Yes. Another example, let us take see Z1, Z2, Z3 are vertices of an equilateral triangle. Equilateral triangle. Then 1 by z1 minus z2 plus 1 by z2 minus z3 plus 1 by z3 minus z1 is what? See, few minutes back, we have got the representation of geometrical representation of equilateral triangle in complex plane. You write as z1, z2, z3 are vertices of an equilateral triangle. Like this. This is the equilateral triangle. This is Z1, this is Z2, this is Z3. Means the distance between Z1 and Z2, is equal to distance between Z2 and Z3 is equal to distance between Z3 and Z1. So this result I can put as Z1, Z2, Z3 are the vertices of an equilateral triangle. Okay. So let it be equal to K. Therefore, I can write Z1 minus Z2 is equal to K. Now square both sides. You see, mod Z1 minus Z2 whole square is equal to K square. Now mod Z1 minus Z2 whole square. What formula should I apply here? The formula which we have done in the last video, last class, Z into Z bar, mod Z whole square. So instead of mod Z whole square, you can write Z into Z bar. So Z1 minus Z2 into Z1 minus Z2 bar is equal to K square. Okay? That is Z1 minus Z2 bar is equal to K square by Z1 minus Z2. Similarly, Z2 minus Z3 K square by Z2 minus Z3 and Z3 minus Z1 bar K square by Z3 minus Z1. So these results you are getting. What should be the next step you follow? Just add them. Means left hand side will be added with all left hand sides and right hand side also be added with right hand side. Okay. So if I add it, I will get Z1 minus Z2 whole bar plus Z2 minus Z3 bar plus Z3 minus Z1 bar is equal to, take K square common, see the required term is coming, 1 by Z1 minus Z2 plus Z2 minus Z3 plus 1 by Z3 minus Z1. So we have got, see, K square, I have added left hand side as well as right hand side. In left hand side, Z1 minus Z2 bar plus Z2 minus Z3 bar plus Z3 minus Z1 whole bar. And from right hand side, I can take K square common, 1 by Z1 minus Z2 plus 1 by Z2 minus Z3 plus 1 by Z3 minus Z1. 1 by Z3 minus Z1. So from this place, I am shifting to this place. What I will do with this? What I will do with the bar sign on the top? I will split up into two parts. Why? Because we are taught Z1 plus minus Z2 whole bar, Z1 bar plus minus Z2 bar. Okay? So this thing Z1 plus minus Z2 whole bar, Z1 bar plus minus Z2 bar. So from this result, what I can get? You see, therefore, Z1 minus Z2 whole bar, you write this part, Z2 minus Z3 whole bar plus Z3 minus Z1 whole bar k square into 1 by Z1 minus Z2 plus Z2 minus Z3 plus Z3 minus Z1. Now, according to this rule, Z1 plus minus Z2 whole bar, the splitting of the conjugate part, conjugate sign, I can split up each term. You see, Z1 minus Z2 whole bar, Z1 bar minus Z2 bar plus Z2 bar minus Z3 bar plus Z3 bar minus Z1 bar is equal to k square 1 by Z1 minus Z2 plus Z2 minus Z3 plus Z3 minus Z1. All terms will get cancelled. That will give us what? This whole thing is equal to 0. Therefore, k square 1 by Z1 minus Z2 plus Z2 minus Z3 plus Z3 minus Z1 is equal to 0. Now, k square cannot be 0. Why? Because k is the length of the side of an equilateral triangle, which cannot be 0. As k square cannot be 0, therefore 1 by Z1 minus Z2 plus 1 by Z2 minus Z3 plus 1 by Z3 minus Z1 is equal to 0. Okay, so we were able to do the sum with proper elaboration. Don't overstep, don't jump any step. Mainly in board level, in joint entrance, you can jump step, but in board, you show all the steps. If you show all the steps and if you keep yourself in touch, in touch with this type of procedure, your knowledge level will be increased. Okay, your knowledge level will be increased. You will get a good craft throughout the throughout the chapter. Hope you understood. I'm rubbing this sum. I'm going to skip to the next property. Now, for your convenience, I'm just giving you two formulas. You have to learn these formulas. X square by factorial 2, cos x is equal to expansion of cos x. 1 minus x square by factorial 2, x to the power 4 by factorial 4, minus x to the power 6 by factorial 6, infinity. You can get this expansion by doing the Maclaurin's theorem, means the application of derivative. And sin x minus x cubed by factorial 3, x to the power 5 by factorial 5, and so on. Now, e to the power x, 1 plus x by factorial 1, x square by factorial 2, x cube by factorial 3, x to the power 4 by factorial 4, x to the power 5 by factorial 5, x to the power 6 by factorial 6, and so on. Now in place of x, I am replacing I, e to the power ix. So all x will be replaced by I, the concept you got in function. 1 plus ix by factorial 1, I square x square by factorial 2, I cube x cube by factorial 3, I to the power 4 x to the power 4 by factorial 4, I to the power 5 x to the power 5 by factorial 5, I to the power 6 x to the power 6 by factorial 6 up to infinity. Now you complete the calculation. I square is minus 1, I cube is minus I to the power 4, 1, I to the power 5, I to the power 5, I cube into I square, minus I into minus 1 plus I, and I to the power 6, I square whole cube, minus 1 whole cube, minus 1. So these results they'll use these results, then 1 ix by factorial 1, I square is minus 1, so this is minus x square by factorial 2, I cube minus ix cube by factorial 3, I4, I to the power 4, 1 factorial 4, I to the power 5, again I, x to the power 5 by factorial 5, I to the power 6 minus 1, and so on. Now here you to express it in complex number, you separate real and imaginary part. 1 minus x square by factorial 2, x to the power 4 by factorial 4, minus x to the power 6 by factorial 6 up to infinity are kept in a bracket, and from the rest take I common. Factorial 1 is 1, x minus x cube by factorial 3, x to the power 4 by factorial x to the power 5 by factorial 5, and so on. So this has become cos x. You see, you have got this property few minutes back, cos x plus I sin x. You have got cos x. Cos x is this result, plug the value and put here. Sin x is this result, put here. So e to the power ix is cos x plus I sin x. Hope you understood. So this result you note down, important result, that is where to apply this result. Having this part, see, you got the property, means polar form, r cos theta plus I sin theta you got last day in polar form, where theta argument of z. Now few minutes back we have got e to the power ix cos x plus I sin x. So instead of this I can write e to the power I theta. So this is a form, standard form. It is called Euler's form. Euler's form. In complex number, this form is called Euler's form. So if you get 2 points, then say z1, then r1 e to the power I theta 1, okay, and z2 r2 e to the power I theta 2. Okay, means one angle is theta 1, another angle is theta 2. Now multiply z1 into z2, r1 into r2 will be multiplied, and you see log of exponent, base same, power different. I theta 1 plus I theta 2. What result that will give? R1 R2 I theta 1 plus theta 2. That means, therefore, Z1 Z2 will be actually, write it again in polar form, R1 R2 cos theta 1 plus theta 2 plus I sin theta 1 plus theta 2. Okay? So if you put a bar sign on the top, means if you want to find a conjugate, this plus will become minus. So R1 R2 cos theta 1 plus theta 2 minus I sin theta 1 plus theta 2. That is Z1 Z2 whole bar. Okay? Now Z1 we got R1 into e to the power I theta 1. So you rewrite it in terms of polar form. R1 cos theta 1 I sin theta 1. So what is Z1 bar? What is Z1 bar then? R1 cos theta 1 minus I sin theta 1. So instead of this, what can I write? R1 cos, you know, you basic property of trigonometry, cos of minus theta is equal to cos theta. So cos minus theta 1 plus I sin minus theta 1. I have expressed it with the general expression of polar form, it's in plus form. So this can be expressed as, see, I forgot to write, put bar sign on the top, e to the power minus I theta 1. Here theta 1 is negative. Okay? Similarly, see, if I get Z2 bar, write similarly Z2 bar R2 e to the power minus I theta 2. Okay? Now multiply Z1 bar into Z2 bar. You see R1 and R2 will be multiplied and base same power different I theta 1 plus theta 2. What do you mean by that? You express it in terms of polar form. R1 R2 cos theta 1 plus theta 2 minus I sin theta 1 plus theta 2. So Z1 Z2 whole bar is equal to Z1 bar into Z2 bar. Z1 Z2 whole bar represents the value which is also represented by Z1 bar into Z2 bar. So I can write Z1 bar into Z2 bar, Z1 Z2 whole bar. So I told you that Z1 plus minus Z2 whole bar, then the splitting of the bar sign also be applicable in product, and that will be discussed in later. I told, and see, by using Euler's method we could discuss it. Okay, now division. In division, that is the special privilege of complex number, that is division. That is not allowed in vector and coordinate geometry, only in complex number. That's why complex number is one step ahead, advanced version of vector and coordinate geometry. You see, division. Bracket. See, e to the power ix cos x plus I sin x. So in the same manner you will get e to the power minus ix cos x minus I sin x. Now you see Z1 is a complex number in polar form. Cos theta 1 I sin theta 1. R1 e to the power I theta 1. Okay. Z2 cos theta 2 I sin theta 2. R2 e to the power I theta 2. Now if I divide Z1 divided by Z2. So R1 e to the power I theta 1 by R2 e to the power I theta 2. See R1 by R2, see base same power different. I theta 1 minus theta 2. Plus Z1 by Z2 we have got. Understood? Now, if you express it in polar form again, R1 by R2 cos theta 1 minus theta 2 plus I sin theta 1 minus theta 2. Okay? Therefore, Z1 by Z2 whole bar is equal to this plus sign will become minus sign. R1 by R2 cos theta 1 minus theta 2 minus I sin theta 1 minus theta 2. That is Z1 by Z2 whole bar. Now, like previous procedure, what is Z1 bar? Z1 bar is R1 e to the power I minus theta 1, because it will be minus, then you see cos x minus I sin x e to the power minus ix, and Z2 bar R2 e to the power minus I theta 2. Now, in the same manner, you divide Z1 bar by Z2 bar, R1 by R2, laws of exponent I theta 1 minus theta 2. That means R1, see, little bit clumsy, it becomes e to the power minus I theta 1 minus theta 2. That will give you the same thing which was already represented by Z1 by Z2 whole bar. Cos theta 1 minus theta 2 minus I sin theta 1 minus theta 2. So Z1 by Z2 whole bar is same as Z1 bar by Z2 bar. So Z1 bar by Z2 bar is equal to Z1 Z2 whole bar. Hope you understood the proof. Important proof, that is concept builder, application of Euler's form in complex number. Okay. So what thing we are taught today? In summary, let us discuss. I'm rubbing this part. Hope you understood. What thing we are taught today? We are taught that if two complex numbers resultant or difference is taken with Barson in the top, then it can be broken into two parts. It is true for product. It is true for product Z1 bar into Z2 bar. It is true for division Z1 bar by Z2 bar. It is true for product. It is true for the division. And we got the distance between 2 points. This is distance between 2 points Z1 and Z2. Hope you understood. Hope you understood. And last day we got Z into Z bar mod Z whole square. We got Z bar comes twice, and again it will give you Z, and we got the polar form of complex number cos theta plus I sin theta. R is the mod Z, theta is argument of Z. It is the polar form we are taught. Today we have got Euler's form. Today Euler's form of complex number R e to the power I theta. So these are taught till now. In one video or two video, the whole chapter cannot be covered. So in next video, the remaining part will be covered. I think it depends. It depends on the depth of the topic. You understand? Here we have explained it with, you know, thorough explanation. I did not jump any step, and see, in each case I have shown you how, from where the formula has come, where did we get that formula. It is not the bunch of alphabets. It's behind the establishment of this formula. There is some, you know, explanation, logic. Without explanation, logic, mathematics will not stand. Hardly you can get the fathom of this chapter. Understand? So in next class we'll go through few sums, cube root of unity, and De Moivre's theorem, and the application of this. Okay, so no more today. Till then, goodbye. Have a good day. Thank you.